Hello, I am Amitov, and this is my blank home screen. This is my editor, and this is tinygrad-verilog. So, I just finished implementing the forward pass. So basically, now have the ability to define like number of neurons per layer and number of layers in a network, define weights and biases for those, and then like basically pour in a bucket of inputs and get out like some outputs, which is cool. I mean I can show it off right now. Make tests network. You can see inputs 1, 2, outputs 2.918, 2.195. Now for this test we had no intended output, but what I want to do like in this work session, I guess, is get training working, because like nobody cares if you can just take in a number and get another number. Cool, like I can do that with addition. 5 plus 2 equals 7. Wow. What we want to do is have numbers like that come to where we want them to go, right? And the way we do that, as I guess, I don't know if it's implied or explied, grad, the way we're going to do that is by calculating the gradients. So before we get started like with the actual code stuff, I'm gonna figure out like how we're actually gonna implement this in hardware, because yeah, seems odd. So I am actually going to cheat a little bit. Sue me. Last summer I made this project where I implemented AutoGrad, and I already have like in C++ a whole bunch of, basically I have just like automatic differentiation implemented. So we can basically take this and figure out how to translate this into hardware. So let's, I guess, let me change this to here, and then is there like something that uses this? Neural networks. Okay, so this was my data set before. Well, the function we were trying to fit, y equals 2x plus 1. Now this could really be any function. We could use a more complex function because ours supports multiple layers, but just for simplicity, let's just let's start off with backpropagation for a single layer, single neuron neural network. So if we sketch out the architecture, we have our input, then we have our network. For now it's just this single neuron, and then we have our output. So for clarity, I'm going to label this as inputs, outputs predicted, and this is in contrast to output true. So let's choose some random number, okay? Let's say that our input is 3. So our true output, so 2 times 3 is 6, plus 1 is 7. So output true, I don't know. I think like in the literature, the notation they use is hat for the true value. So it'll be less clunky to just do y and then input x. Make sure like that is the notation we are using. So y hat is equal to 2x plus 1. So given x equals 3, y hat equals 7. Now let's just make up a weight and a bias for this neuron. Let the weight be, I don't know, 0.7 and the bias be 2. So now let's compute the forward pass with these numbers. So given x equals 3, y is equal to, so first we multiply the weight 0.7 by the input 3, and then we add the bias. So this is equal to 2.1, here 2.1 plus 2 plus 2, which is equal to 4.1. So now after this we usually have a ReLU, which is just like, wait, no, I think that terminology is off. We have our activation, and the activation we use is so maybe here activation x, so it's x if x is greater than 0, otherwise it's 0. 0x is less than or equal to 0. So this is just, there's probably some reason we applied activation. Not entirely sure right now, but I mean, I'm sure we can Google it. Why do we apply activations to neuron outputs in neural networks? Activation functions in neural networks. An activation, it introduces nonlinearity, enabling the model to learn and represent complex data paths. Without it, even a deep neural network behave like a simple linear regression model. Whether a neuron should be activated based weighted sums of inputs and a bias term. They also make backpropagation possible by providing gradients for the weight updates. Is rarely linearly separable. Okay, curved decision boundaries. Consider a neural network with inputs I1, I2, hidden layers So neurons H1 and H2 and output layer 1 neuron output. So W1, W2, W3. What? This diagram appears to be wrong. The oh, you can't see my cursor. That's not very fun. Yeah, the connections. So hidden layer outputs are, okay, the output before activation is H1. Output before activation H1 times, I assume. Yeah, that's odd. Without activation, these are linear functions. We apply a sigmoid activation. We do not apply sigmoid activation. What? Sigmoid. Here, ReLU. I'm going to use ReLU just because it's easier to compute by hand than all these other ones. Yeah. So, now we know why we apply an activation, so that our models can learn nonlinear functions. So now, we could apply, this is equal to activation x because it's greater than 0. So cool. Our output is 4.1. Now you can see over here y hat, the value we were supposed to get, is 7. Now 7 and 4.1 are different numbers, so our model has made a mistake. Now, our goal is to get this thing as close as possible to this thing, and I'm going to show you how we do that. So if I head back over here. So simple data set, okay, cool. That's interesting. LSP. Import. Amazing. I love language server protocols. Language server protocol. So, for this, we have a struct node with a value, a gradient. Take note of this. That'll be important. A backwards function and a list of children. So, you can see here that our weight and our bias are each different grad.cpp. Our weight and our bias are each separate nodes. So now, okay, that's actually really annoying. Here, these are our parameters, our weights and our bias, and then, holy moly, 5,000 epochs. Interesting. What is this indentation? That I have no idea how I worked in this. Okay, so let's now walk through what the epoch looks like. So our lots value starts at 0. Makes sense? So now for each parameter, we make the gradient 0. That also makes sense because the gradient tells you basically like simply how much you've messed up, and you can't know how much you've messed up until you've actually messed up, and you can only mess up once you've actually done the thing. That feels philosophical in a way. Here, okay, so then we have a for loop. So this looks like it's looping through the input. What are these errors? I don't care. Here. So new node x equals new another node with the data of the corresponding elements over here. Now you may notice this says matrix. I am guessing that, yeah, we have one size 1 by 1 matrix. Odd. And then we have another node with our true y, and then the forward pass. So we matrix multiply the weight and the inputs, and then we add that product to the bias. That's all. I wonder if that's actually correct. That's odd, because I'd thunk. When computing a forward pass for the a neural network, should you Hadamard? So that's like where you element wise multiply like element 1 1 of one matrix by element 1 1 of another, and so on for the rest of the matrix. Product the weight and the input, or matrix multiply. Explain why. Because like element wise multiplying seems more intuitive as like a weight, because you're actually matrix multiply. Interesting. Okay, so we have a 3 by 2 and then a 2 by 1, 2 by 3 and 1 by 2. I think this matrix, this vector is formatted incorrectly. But yeah, that sort of makes sense, I suppose. Yeah. Cool. What were we talking about again? Right. We were walking through this. So now these are custom seems overselling it. Like, these are not like standard library. So let's walk through this. So the matrix multiply function takes in two nodes, well, pointers to two nodes, and then okay, so just like looking ahead here, we return z. So z is important. So z is a new node, x value times y value. So if I remember correctly, I think this is here math primitives vector.hpp operator. I think we're doing operator overloading here. So if I vector.cpp operator this, okay, so for int I is less than what? Guess we're assuming these are square matrices? Wait, matrix. Would it be here? Matrix definition. This is the wrong file. Vector.hpp matrix class matrix. Okay. What does size do? Using my list math vector size. Math vector size. Using my list float my list, and then I think okay, so the size R1, this is just the height of the matrix, because the way this matrix is implemented is it's just a vector of vectors. And then over here, this is the size of the first vector in that vector, so that would be the width. And then this is other dot size, and this is other zero dot size. So if C1 is not R2, okay, that's just because I think it's like if I have two matrices, then the way we multiply is like height L by width M by height M by width N to one matrix with height L and width N. Yeah, so if these two numbers are not the same, then it's undefined. Okay, so matrix, so we transpose the other matrix. Interesting. And then, okay, row A is this. We loop through every row. And then, okay, we have row over here. And then we push the dot product. Why? If I remember, if we have two vectors, u dot product v, that is a really bad v. This is equal to the sum I to n, where n is like the length of each vector of u I v I. So this would dot product row A. So this would dot product take the dot product of, let's say I have some matrix, let's just say A, B, C, D, and then matrix multiply E, F, G, A. What this would do is, so first we would take this row is equal to, and then take the dot product of this row with this column. So by the definition we saw earlier, that would be AE plus this multiplied by this, BG. Then we would take the dot product of this with the next column. So AF plus, man, I really hate that this, well, hate is a strong word. I dislike that this is not showing my mouse cursor. Ooh, turns out it was just a little toggle. The E, F, G, this should be D. Wait, what? A, B, C, D, E, F, G, H. H, right. AF plus BH. Is this correct? Yeah, because we, wait, what? First we transpose it. Here, let me just undo a bunch of this. So this is equal to we transpose this, so in this case that would mean swapping these two elements, and then we continue. So this row by this row, so that would be AE plus, because we swapped these, plus BG, and then this element would be this row dot producted by this row, so that would be AF plus, why is this H? Why is this not H? Sorry. H, so AF plus BH, again F because this swapped, and then moving on to the next row, it would be CE plus DG, and then CF plus DH. Why were we figuring this out? Right, because I was trying to explain. Okay, so then you can see, like, if you imagine AE and AF. Yeah. Right, let's get back to what this was. So let me head back to main.cpp. So we take the matrix multiplication of the two values. So in this case, because they're both 1 by 1 matrices, that would just be the same as regular multiplication. So because they're zeros, that would just be 0. What? Is that true? No, that would be the input, which is not 0. The input for the first go through would be 1, multiplied by the way to which on the first pass through is 0. So we have our new node set, and then this is interesting. We actually push to the children of Z X and Y, and then we're defining our backward function. So x grad is equal to x grad plus z grad times y value dot transpose. Why are we doing that? Time for some here. So we're saying z is equal to x. Sorry, the notation there is bad. These are bold because these are matrices. So that'd actually be like, I'm just gonna there, and times z equals x times y. So what we're trying to do here is find what is that symbol like? The fancy D. I don't know. Like, I think it's, so we're trying to that's a 6. Hopefully that's correct. So we're trying to find how the change in z with respect to the change in x. Now you can imagine this as basically figuring out how much is x to blame for this. Because if we know how much x is to blame for it, we know how much to like change it so that next time this will be less. Right? I hope that makes sense. So for something like this, I'm not sure how you would let's I don't know, zip back up here. So I don't know, let this be just x for the sake of this example. So where are, well, there's one of our variables, there's another one of our variables, there's one of our variables, there's another one of our variables, there's 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 one of our variables. So what is it, like d over df over dx equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So in this case we're substituting f for z, right? Correct. So I mean, like, you can look at z sort of as like a function of x and y. These should be bolded. Yeah, so if we do that, we get, like, here. This would be, because there are two variables here, what we do is we treat, like, all of these variables as basically just as, like, constants. So the change in z with respect to the change in x, like, these imagine, like, these are all 3, like, if f of x is equal to 3, the difference between f of 3 and f of 4 is 0. So the gradients, the derivative of f with respect to x is 0. So now when we're finding, like, partial derivatives like this, where there are two variables, we do this by literally just we do this by just imagining all of these are constants. So change in z over change in x is equal to the limit as h approaches 0 of, so I'm not sure how you would substitute that. So let's rewrite this as z of x, two matrices x, y is equal to x times y. So now when we're finding this change in z with respect to change in x, we can just, so this is equal to the limit because we're finding a partial derivative, we're also just basically imagining this is only a single independent variable. I don't know if that's the right terminology. This is constant for our purposes. This is the reason we differentiate both with respect to x and with respect to y, because then we know how much both I guess both of them messed up in a way. So then this would be just x. Well, x times some constant c. So then the limit as h approaches 0 of, I guess in this case h would have to be another matrix. Well, no, I don't think it has to be. You could just have it be sort of let's just say that when we add a scalar, we're just adding that scalar, that single number, to every single element of the matrix. So z of x plus h minus z of x over h. So this is equal to the limit h approaches 0 of, well, because we're multiplying by y, this should be y of x plus h minus just y of x, right? And then h so I guess you could factor out x here. So this is the limit as h approaches 0 of, because multiplying all of this, oh wait, no, but this y, so this is equal to y x plus y h minus y x over h, and then these cancel out, right? So here these cancel out, so that means we're left with the limit as h approaches 0 of y yh over h, and that, now these two cancel out, so we're left with the limit as h approaches 0 is equal to y. which is now equal to y because h is missing an action. So that's cool, I suppose. Why do we multiply by the gradient of z though? Oh, okay, yeah. So when we're performing the backwards pass, we multiply. I think we multiply like if x grad is equal to, I don't know, some number, and then y is like, I don't know, x children is y, we multiply, I think we multiply y's grad, or no, we factor, like, we insert x's gradients into the calculation because why do we do that actually? Well, I suppose it's because if by like propagating, like letting the sort of gradients from a parent node affect the child node, we've already determined when finding the gradient for the parent node, this is how much, like, if you imagine this as like a tree, right? So at the root node, this is just the loss, and then we have like our tree going downwards of, in our case, the node below that would be like this is y, I guess y and y hat. We wouldn't differentiate with respect to y hat though, because that would make no sense because we can't like change the expected outputs. And then like from here we have like, if you imagine in like a multi-layer, or I suppose, so from y it was like we had like our bias, which was, and here bias, and like this is xw, and then from here we have x, and over here we have w. So in practice we only differentiate with respect to, like, we only optimize these parameters because like it makes no sense to optimize the inputs because you don't control the inputs. You only control what you do with it. Yeah. So now if I've determined that overall, like, this node has, I don't know, it's like 0.6 to blame, right? So then I know, like, I can figure out how much each of these parameters are to blame for this parameter, and then you can like sort of merge those two blame numbers together to get like the blame for any, like, not root, I suppose it'd be like roots maybe. I feel like this would be the roots though. That doesn't matter. Yeah, I hope that like sort of makes some sense. We spent like a lot of time talking about like not actually implementing this. So yeah, it's pretty much the same idea for most of the others. I'm not going to like figure out the gradients by hand for them because that seems like a waste of my time. I'm sure like these are already out there on the internet or whatever. So yeah, and then like you can see with add, we add the gradients of xgrad equals xgrad. Yeah, that's because if you imagine like z of x comma y is equal to like x plus y. Another way of like saying differentiating is like if I nudge this by some amount, can I predict how this output will change? And the reason that this is useful to know is because then I can say, well, I want to change this by this much, so I must have to nudge this by this amount. So if you know how it goes one way, you can like go the other way. Yeah. That's cool. And then forward pass, we compute like the loss using mean squared error. And I see here. Okay, so there are actually quite a few nodes used here. For int j, so for each of the rows and for each of the columns. Scale. Odd. Okay. This is just the error, and the gradient of each of our predictions is we add like that and that. Then here we initialize the gradient to the final node to 1, 1. This is because, like, how much is, like, the loss to blame for the value of the loss? Well, the loss is 100% to blame. Because, like, if you nudge the loss by 1, the loss will also go up by 1 because the loss is the loss. I said that quite a few times. What the hell? I think this is just some bad code. Here, now let's go to the backward function. Well, there are a bunch of backward functions, but like this specific one, it's actually surprisingly short, but it's pretty cool actually. So when I call backward on this node, so let's say I call backward, right? So now if it has a backwards function, it runs that function. So like from earlier, you saw all of these functions basically chain, like all these backward functions calculate the gradient of that node. And then what it does is it goes through each of that node's children and it calls backwards for those nodes' children, for those nodes' children's? Child's? And then I just wonder, like, it looks like when we run this, both of these functions return. That returns a node. That also returns a node. This node is the result of this function. This node. I assume that the node is like still around, because instinctively I'd think like once we finish this add, you know, it'd just be like not mutilated. That's a really brutal word to use for that. Disposed of. But I suppose not. So this is your softmax, that's different. So this is MSE. Okay, so this is interesting actually. This node, when you call this function, it returns a node, but it also creates a bunch of like new nodes. Diff interesting. Okay, let's we've been sort of meandering. Let's get to the actual Verilog. This is not Verilog. Here. Okay. Let's get started, I suppose. So, to calculate this, the gradients of all the nodes, you need to store the intermediate states, I believe, which is great because we already do that in the forward pass. So if I come to here, you can see, bam, intermediate states. So let's figure out how we translate this, which is very like abstract, you know, functional wahoo, into like hardware. So would it make more sense to define like a so I was going to say, like, would it make more sense to define like a backward function for like when initializing each neuron, but I assume if like you know the architecture, like if I know that this is what like I don't know what color to use, green. If I know this architecture a priori beforehand, and the way we have it set up is that it's actually the test bench, like we get fed in all of the weights and biases. So you could make a separate, mostly unrelated module where you just give it, you know, the number of layers and number of neurons, and then from there it figures out the gradients of each neuron. I hope that makes sense. Think like I should probably just start coding, and then if it doesn't make any sense, we can backward.v module backward hashtag parameter n equals 4, parameter m equals 4. Here, do we need a clock? Probably, because we have to like iterate through each of the, yeah, I think so. Let's try to build it without a clock to begin with, like if we can do it purely combinatorially. That's a really fancy sounding word. Combinatorial. I'm probably pronouncing it incorrectly. Anyways, right. What we want to do is so we want to take in input wire signed we want to take as an input this, And this, what do we want to output? That's a real question. I suppose, I mean, we want to output like gradients? But what does that mean? What does that mean actually though? Here, optimizer, SGD. Here. Gradient descent. Parameters equals params I minus learning rate dot grad. Reset gradients to 0 after update. Okay. So we want to take these in as inputs, and we want, so input, we need like, do we need the actual inputs? Like, I don't, yes, I think we do, because over here, like, you multiply the input by the weight, like by this thingy. Sorry, we multiply the inputs and the gradients of like this thingy includes this other term inside of it. So x weight bias loss, then we want to return gradients. Capiche? So also, in addition to this stuff, it would also be beneficial to have the intermediate states. Because if we, like, imagine, I don't know, let's just sketch out, I don't know, let's say we have a neural network that has inputs, you know, 2 inputs. Let's just sketch out our neural network. So think, I call this 2 hidden layers, but I think it would actually just be 1 hidden layer, because this would be the output layer. I don't know, it doesn't really matter. You can Google the terminology if you'd like. Here, here. So can we like just compute a forward pass? So for simplicity, let's set weights to, I don't know, ones, because I can't really be bothered doing multiplication. And then biases also 1, and let's say that it's just the same function as earlier. So our input is going to be 3, and our expected output is 7. This, I highly doubt this will produce the correct. Oh wait, this doesn't make sense because we have 2 outputs. can we... And we have 2 inputs. Okay, I suppose we could just have it be like 3, 4, and then 7, 7, 9. So let's get started. H1 is equal to, if we look over here, so that would be, let's W0 to W7, so that'd be weight 0 times x0 plus W1 times x1. I suppose for consistency, let's call this H0, and then H1 is equal to W2 times, well, plus B0, then W2 times x0 plus W3 times x1 plus B1, and then, okay, and then going forward, so this is H2, this is H3. H2 is equal to W4 times H0. Technically this isn't hidden output, but nobody cares. Plus W5 times, this doesn't make any sense. Wait, no, it does. Okay, plus W5 times H1 plus B2, and finally H3 is equal to W6 times H0 plus W7 times H1 plus B3. Cool. These are our outputs. So now these are 1, so these are, like, all the weights cancel out. So we get x0 plus x1, so that would be 7 plus b0, so this is 8, this is also 8, this is 17, and this is also 17. Cool. So this is our forward pass. Y is equal to 17, 17. 7, comma 17. So now this looks sort of painful. We will calculate the backward pass. Let me see, like I did earlier over here with that, can I do something similar with this one? So we have our two, I didn't apply activations here, but that doesn't matter because the activations would not have changed anything because nothing went below 0. So x1 x 0. Let me drag this up here. So what's the cleanest way to do this? Clean doesn't matter. Here. So W0, I'm not gonna bother like putting bubbles around them because that is too many bubbles. W0, W1, W2, W3. So good enough. Okay, so here, drag this over here. This times this times this, and then plus, and then this times this, and then another, multiplication, this, wrong node, this times this, and we add these two together, plus, and then we have B1, B0, and then plus here, plus. So now this is the end of our first layer, first hidden layer. Well, only hidden layer, technically. Yeah, this is going to take a long time to calculate. I am not completing this. We should probably just get started on the actual programming. So, well, yeah. So, like, we extend this forward, and then during the backwards pass, here, maybe feature. Okay, so I think I already have. Yes, I made this at lunch. This is the wrong file. What the hell? Here, backward.v. Then we have our terminal. So, let's actually ask Claude. Hey, Claude, what would be the cleanest Sorry, it's just like weird. I'm looking up here, so I have my second monitor where I have like OBS on. Sometimes I'll like glance back down and I'll be like, oh wait, it's this over here as well. Sorry, that's irrelevant. What would be the cleanest way in which to implement backward pass for this project? I'm thinking, because we know the architecture a priori and we store all of the intermediate states, we could just modify the at network.v to also output the intermediate states, and then create a separate script through which we run the backwards pass. Also, this would be pretty easy because we feed in the weights and biases to the network during runtime. Let us see what Sensei Claude has to say. Here. Intuition is solid. Shut up, bro. Here, recommended approach, expose intermediate states. Create a separate backwards.v. So activations, weights, loss gradient. Wait, I don't. What? 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 For a hill and kill, why did you not know? Cause I'm chill deep inside.
Okay. Well, you have a meeting?
Here, I'm just recording a video.
Okay.
Yeah.
Everything is okay?
Yeah.
Okay, good job.
Ah. Darn it. Just like last time, turns out these headphones are still connected to my phone. I did not need to have them in for the last... We've been on for an hour and 20 minutes now. Cool, lost screen. Would this not just be a... Is that just one? What? Ah. Here. These are some fancy words and fancy symbols. Yikes. For cool. So let's get to work on that. Layer.v. So what we want to do is pre-activation. Do we? Nope, we do not, because that's handled by the neuron. So if we want to do this, we're gonna have to like remake pretty much our entire interface. yes, I took a look at there.v. Looks like it doesn't expose pre-activations either, because those are computed in neuron.v. It looks like we would have to output pre-activations from the neuron to the layer, then from the layer to the network. So we will have to rewrite much of our current interface. Interfaces, I suppose. Okay, I just, like, didn't, like, spill water, but, like, I don't know, the water went like that, and then some water came at the top. Okay. For ReLU specifically, you don't need the pre-activation value. That is very handy. Okay. So, good news, because we're using ReLU, as Sensei Claude has told us, oh, sorry, it's like just a nice book I had on my desk and there's water on it. Doesn't look that wet. Right, we were, yes, network. That. There. Output wire signed. How big is intermediate states? We can actually just copy this, paste this, and then the only change needed is outputs. I think that's the only change we need. Yep. Because then over here, yeah. Amazing. Okay, now let's save that backward.v. So, let's do this. Input wire clock, input wire start, input wire, I'm just gonna copy this. CT, ooh, shit. Why is that? Why? Is this like all one line? That is here. So now we should be able to there, janky. Here, can we just like, I'm guessing it's because of this. What the, no, it's like multiple lines, or one line or something. This is line 1. Huh. Here, I have like this tool which lets me make a bunch of new, here, random work / scratchpad. Here. Yes, I trust this folder. Why does this didn't work? It doesn't matter. Okay, I copy some text from a tmux buffer inside of vterm, and now when I paste, it's like all one line. I have pasted this into an Emacs buffer. I fix the lines. Fix. Fiddle faddling. Here, I can 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 13, 14. Can I just... No, I suppose I can't. This is going to be annoying. 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 55, 56, 57, 58, 59, 60, 61, 62, 63, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 81 characters. Here. Alt text replace regex slash 80 slash and what if I just like holy okay this what That is some pickle. Claude, continue. Maybe I can just ask Claude to fix whatever this is. Hey, can you fix the messed up indentation in backward.b? Now, yes. Amazing. Okay, so now let's do this. So we are given the loss gradient. The loss gradients, the weights, and the activations. Wait, why don't we feed in the biases to the module? Why don't we feed in? What? Bias gradient is independent of what the bias value actually was. Fascinating. That. What the? Okay. So, could we do this using combinational logic? I assume I don't see why we couldn't, because oh no, you need to show the gradients. We could just make like another wire with like all the gradients. Yeah, it seems simpler, because then we don't have to like, sort of been putting off like actually writing the thing. So I know that it's recursive. I don't know. Always at pause edge. See, okay. Begin. And end. So what we want to do is let's do it using procedural logic. Be easier. How does one do recursion in Verilog? Here. Okay. Yes. Sketch structure for the backward module. Okay. Here, can you edit that? Can you apply those? Edits to backward. So, change, DL, DT, does sub FSM mean? Sub FSM for now. Can you implement the compute DZ state? Cloud is doing good. Yes. Okay. So, so if activation value again equal to DL init DC again I equals 0 state equals compute DC. Okay, so next we compute DZ. C is equal to C is equal to C is equal to X times W plus B. So if the activation value is greater than 0, then where is this thing signed? Here, DL. Okay, so this is the size of transfer with respect to pre-activation. So here, okay, so to compute DZ to DLDAI, we set DLDAI though. Okay, so state is idle done is equal to 0. So in the idle case, done is equal to 0, and then when it receives the start signal, it sets the layer index to m-1. So assume this is going to the final, the last layer. If I go up, layer index. Okay, current layer. Yes, that is correct. So starts with loss gradient dl underscore dA is equal to dl underscore dy, and then it starts in at dz. So it starts the counter, then it sets the state to compute dz. So okay, dl dA I is equal to I, and then so over here I is less than, or I is equal to 0, so this would be this syntax is that when I is equal to 0, this would be dl underscore dA 15 to 0, and I is equal to 1, this would be dl dA 31 to 16, etc. Right? Okay, face, select width. That makes sense. Okay. That's actually quite nice syntax. So okay, so if the activation is post prelude, d is equal to dl dA, so that's the gradient from, I assume, like the previous layer. What is this initialized as? Is it initialized? Yes. Okay, so to start, that is the loss gradients. Okay, so then okay, so after finishes computing this, explain this to me. for back prop through ReLU. And change ReLU said derivative 1 if z is greater than 0. We don't have pre-act, we have post activation. Okay, so if a is greater than 0, z must have been positive. Derivative equals why would we want to kill the gradient if the pre-activation was negative? Explain like I'm a beginner to calculus and to machine learning. So, if we nudge this, how sensitive is my final answer to this particular knob? Okay, that's actually a good analogy. Okay, I understand now. That makes sense. Cool. So what's the here? Okay, so so that's equal to how would assign a, I don't know, certain value to here. Now let's do DW. What's it interesting. Okay, so what is it doing? Okay, there. So let's scroll through this. NATW initialize counters. So it loops through over here. See, it loops through each individual position in the matrix. If j equals n minus 1, begin, and else begin. Here, compute DA yeah, this is odd to me because it looks like yes. Okay, it hasn't finished implementing compute DA. So that'd be the change in activation. Helper for weight layer IDX Okay, so now and init da here. I don't understand how this works. Don't understand this works. Like all compute dw is doing waiting and iterations for handing to init da to just be oh wait, I think I understand. So if I go I don't understand this. dw index password 16 is equal to mult q88 mult q88 mult results dl d said j a prev j compute tw so that's okay, so what does I and j presents again? Context output index okay yeah, where's the test bench? Test bench at runs a single forward and backwards pass. That's the inputs be 1, 2, 3. The outputs be actually we can do better than a linear regression. Be 1, 0, 0, 0. Wait, no, then it doesn't correspond to like the shape of the network. Yeah, it can figure out an appropriate like task. Sure, bro. Ooh. Didn't fail immediately. Is that what it's supposed to be? Whew. Much tokens. Okay. Yes! Okay. We're done. There's a backwards pass. Next time, I still need to like implement the optimizer, and also afterwards we're gonna have to make like the right now the network architecture is really like limiting because each layer has to have the same number of neurons, and that has to be the same as the number of inputs and the number of outputs, blah 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 blah. Yeah, we'll have to figure out some way to specify that. I'm sure we can figure it out. Thank you. Goodbye.